Awesome. So, hi everybody. Welcome to the What Is seminar. Today, Tali Monderer will talk about what is Hilbert's Irreducibility Theorem. So, Tali, whenever you're ready, take it away. If anybody has any questions, since we are in a hybrid setting, please say them out loud because we do not hear, because we cannot see the chat while we are doing this.
Yes.
So, Tali, take it away.
Yes. Do I need to pin the speaker or is this?
Yeah, pin the speaker.
Pin the speaker. Okay, I need to find the speaker for this. So in a moment, wait, don't spoil the lecture. In a moment, we'll begin.
Okay, awesome.
Okay, so I'm pinned. So this is pinned and I'll share screen.
You pinned yourself?
Yeah.
Let's
see. Wait, so I haven't seen the spotlight. Oh.
Okay, no, go to yourself. Tali, okay, no, wait. No, just keep the pin. I guess it should be fine.
Yeah, I think in your versions you don't really have the spotlight.
Okay.
I have no idea why.
Okay,
so now we can start.
Take it away.
Okay. So thank you everybody for coming. So this talk will be about Hilbert's Irreducibility Theorem, which is a tool in, I guess, arithmetic geometry and various branches of algebra. And I'll say in advance that I won't give you an explanation as to why this theorem, which we haven't even stated, is true, but instead I'll try to introduce the theorem and explain its significance and how it works. Okay, so feel free to stop me for any questions you have. And let's start. So let's start with the word irreducibility. So Hilbert's irreducibility is about irreducible polynomials. So let me remind you what an irreducible polynomial is, in case you don't spend your entire workday surrounded by them. So suppose we have a polynomial with rational coefficients. Then if we're allowed to factorize it over the complex numbers, it has n roots, and we can write out their polynomial as a product of linear factors. If we only allow real coefficients, then we don't necessarily have a factorization into linear factors, but we have a factorization into some linear and some degree 2 factors, which at the moment we'll start allowing complex coefficients, then these degree 2 factors will split into 2 linear factors. And the thing is that once we only allow rational coefficients, our factorization of the polynomial can stop at any degree. So we can get polynomials of any degree, which we can't factorize even further over the rational numbers. So the following are well-known examples. So x squared plus 1 can't be factored any further. And x to the n minus 5, and this polynomial x to the p minus 1 plus x to the p minus 2, etc. plus 1, this is called a cyclotonic polynomial. They're all well-known problems of irreducible polynomials over the rationals, which you can't factorize any further. And for this talk, we'll be interested in things that happens over the rationals. So our formal definition of an irreducible polynomial, I'll give it for a polynomial with several variables. So if we have a polynomial in several variables over a field, then it's irreducible if whenever we write it as a product of 2 other polynomials, one of them must be a constant. So this is our formal definition. And why are irreducible polynomials important? So to give you some intuition as to why these are important is that we use them to build fields. So how we do this is, so there's a whole technique to it, which you learned in undergrad or are currently learning or if you're taking the course. But just to give you an example, suppose we have an irreducible polynomial. My irreducible polynomial is x squared plus 1. We can take our ring of polynomials and simply whenever write out the polynomials, and whenever I see a power of x squared, I'll put minus 1 instead. So if I have x squared this will go to -1. If I go have like twice x to the 3, I'll have -2 to the x. And after performing this operation, so I've noticed that one thing happened. So one thing, we suddenly have an element, x, which if I multiply with itself, I get -1, which is the behavior we didn't see previously over the rational numbers. And you can also show that after doing this operation, you get something with a field structure. So I can show you how to invert an element. So if I have an element of the form ax plus b, and after plugging in -1 instead of x squared, I'll always get something of this form because all the odd powers will collapse to something with an x, and all the even powers will collapse to something which is rational. Then I'll just multiply it by ax minus b and divide in the result of this, which is a squared plus b squared. So you should be familiar with this. And if I take an irreducible polynomial and follow this procedure, so for example, I think we need to erase the board, right? Yes. So for example, if I take x squared -1, and I'll do the same procedure. So I'll input 1 every time I see x squared, then suddenly we'll be able to write x -1 times x plus 1, and that will be equal to, let's see, x squared -1, which is 0 if we plug in 1 instead of x squared. So we got a 0 divisor, which is bad. So if you manage to forget, this is more or less how we use how irreducible polynomials yield fields. We won't actually build fields during this lecture, so this was just to remind you why we care. So now let's ask the following question. But by the way, does anybody have any questions? Okay. So suppose I have a polynomial with integer coefficients. And I would ask, what happens if I change just the free coefficient, just a0 in this polynomial? So how will it affect the reducibility or reducibility of the polynomial I started out with? So let's demonstrate with this with another degree 2 polynomial. So suppose my polynomial is x squared. Let's assume x squared plus 0, right? So if I change this coefficient to something which is a square, so a square is an integer such that it is the square of another integer. So I can just write b squared. So I'll change it to minus squared. Then I have something that factors. And if I change it to something that is not a square, then we'll get something irreducible. So our polynomial x squared changes quite a lot. And you can show that if you look at values of a in integer values in a box of length n, then we have like at most square root of n or twice square root of n elements, which can yield a square which is smaller than n. So we have like some constant times square root of n squares in this box. So you can actually see that we have more non-squares than squares. If you do number theory, I bet that you have better ideas as how dense are the squares. So going back to our original problem, let's simply add a parameter to the problem. And let's look at our polynomial, our general polynomial, plus a parameter t. So our question about what does changing the coefficient due to the polynomial is basically a question about what happens after we substitute a value in this parameter. Like which substitutions will yield a reducible polynomial and which substitutions will yield an irreducible polynomial. So Hilbert gave a theorem that will assist us with this. And the theorem states as follows. States, suppose we have an irreducible polynomial in two variables, t and x. Then there exist infinitely many substitutions in the parameter t, such that after the substitution, our polynomial remains irreducible. Okay? So just to compare, if we would have, and this is called Hilbert's Irreducibility Theorem. So just to compare, if we would have started as a polynomial that's written as the product of two other polynomials, then it makes sense that, but usually, unless something like really bad happens and we get a really trivial case, after substituting a value in t, we would still get a product of polynomials. Okay, so this is why with a reducible polynomial, we won't have a chance of this. So let's see. Going back to our motivating question, so if I take my polynomial f of x plus t, then this is an irreducible polynomial in the two variables t and x, because it's actually a linear polynomial in t. Like we won't be able to write out any two polynomials which will somehow give us something of this form and won't be involved in the variable element. So it's an irreducible polynomial. And by Hilbert's irreducibility theorem, we have infinitely many integral substitutions that will preserve irreducibility. Okay?
Can I ask something?
Yeah.
So when you plug in specific t0, you now get a polynomial in one variable, right? And
Yes.
you say that now this is irreducible.
Yes, exactly. So we kind of like move from the world of two variables to the world of one variable. Okay? And okay, so I'll quickly remark that you should be like mildly surprised, because if I have a polynomial f of x, then let's write f of x minus f of 1, for example. Then when I plug in 1 in this, it's reducible because it has a root. I can write it out as a linear factor times something. But Hilbert's irreducibility theorem somehow tells us that even though I can come up with this example, and frankly, I can do the same thing if I plug in 2 or 3 or anything of that sort, I can still find infinitely many irreducible specializations. So, so to summarize, what we did was we had a problem, we added a parameter, and then we investigated what happens after we substitute that into the parameter. And in a way, this also gives us kind of like a way to like families of solutions in a way. Okay, so how are we on time?
Oh,
Sorry.
You have 45 minutes.
I have 45 minutes. Okay, so do you want to see another example of the use of Hilbert's irreducibility theorem? Yeah. Okay, so let's try the following thing. Suppose I give you a polynomial with integer coefficients, such that, okay, so you can see this. I can move it. Let's see. Yeah, thank you. Okay. So suppose I give you a polynomial with the following property. So suppose we have a polynomial with integer coefficients, such that when you plug in all the integers, what you get are squares. Then show that this polynomial itself must be the square of another polynomial. Okay, so let's look at this for the other way around. If I have a polynomial, I don't know, h of x, and I look at it squared, then whenever I plug in an integer, I'll get an integer, and overall we'll get the square value of an integer. Now the question is, suppose we have a polynomial that we don't know how it looks, but we know it has infinitely many, like if we plug in all the integers, each one of them yields a square, then show that this is the only case. There must be some other polynomial that our initial polynomial is the square of. So Hilbert's Irreducibility Theorem gives us this very quickly because we just so we just look at the polynomial t squared minus f of x. So if this polynomial is irreducible, we would have had infinitely many integer specializations such that it remains reducible. But if we write something like t squared minus f of I, and we know that this is a square, then the polynomial splits. So in fact, we know that for all integer specializations, this polynomial is reducible. So the initial polynomial with the two variables had to be reducible. But the initial polynomial is, again, something of the form t squared minus something, f of x. So the something must be a square. We have to get the factorization of the form t minus some g of x times t plus some g of x. So this is kind of a toy example that shows the power of Hilbert's Irreducibility Theorem, because apparently this is something which is hard to prove otherwise, but Hilbert gives it immediately. Okay, so let's see. Okay, so initially, when Hilbert stated the theorem, he was interested not exactly in preserving irreducibility. He did it in the context of a different algebraic property, a stronger algebraic object that we can associate with a polynomial, and this is the Galois group of the polynomial. So I'll give you a very quick introduction to Galois groups. So how can you give a very quick introduction to Galois groups? So we'll do it as follows. I'll give you some intuition as to what the idea of a Galois group is, and then I'll give you some examples, and we'll define nothing formal. So this is how we will get a very quick introduction to Galois groups. So the idea behind Galois theory is as follows. By the way, does anybody have any questions? Since you're bracing yourselves for Galois theory, right? Yeah. Okay. So suppose we have a polynomial of degree f. What Galois theory does is we get a permutation group on an element. So n is the degree of the polynomial, and we call this group the Galois group of f. And so we simply, what one normally does is we imagine our polynomial. We say, hey, this polynomial has roots alpha 1 to alpha n, and then we have a permutation group that switches all those alphas around. Okay? And properties of the polynomial translate to properties of the group with it. So the way this will go is as follows. This is how we will prove that a group is a Galois group. If I give you a polynomial, and I give you its roots, and I give you some group that acts on these roots, you will believe me that the group is the Galois group of the polynomial, okay? Do not attempt this at home, but for the purpose of this lecture, this is what we'll do. So there's one Galois group which you've seen. Let's look at our favorite degree to polynomial, x squared minus 1. If you'll notice, all our polynomials are either of degree n or of degree 1. Then let's look at, for a change, this polynomial over the real numbers. We know it has two complex roots, I and minus I. And let's look at the conjugation map from the complex numbers to the complex numbers that takes an element to its conjugate. So this conjugation map takes I to minus I, and so it takes a root to a root. And we know that if we apply conjugation twice, we get the identity back. So the group generated by the conjugation map is the conjugation map and the identity. So we have a group, and it sends a root to a root. So per our agreement, the Galois group of the polynomial x squared plus 1 over the real numbers is the cyclic group of order 2. So I'll note that what lies beneath technically for the definition of the Galois group is you need to look at some field where all the roots of the polynomial live, which is what we did here when we moved from the real numbers to the complex numbers. But we aren't interested in technicalities, so this is the Galois group you see. Now, what do we mean when we say that properties of the polynomial are encoded in properties of the Galois group? So let me give you two examples. So the first one is that the polynomial we started with is irreducible if and only if this permutation group is transitive on the root. So transitive means it can send, so if we have a group acting on these alpha 1 to alpha n, so transitive means that we always have an element of the group that sends any alpha y, alpha I to any alpha j. So we can go, so we can get all the, go from any one root to any other root. And the other example of properties of the polynomial are encoded in the Galois group is the example which made the theory famous. So it turns out that if our polynomial has some closed formulas for the solutions, like for example, a polynomial of degree 2, you have this formula for the two roots of it, then it turns out that this happens if and only if the Galois group has a certain structure, which is called solvability. So we won't discuss this, but this is the famous example. This is what made Galois theory. Let's see. So now that we've convinced ourselves that we know what a Galois group is, we can ask, does substituting a value, given a polynomial, does the substitution preserve the Galois group? Okay, so again, we have our world of polynomials in two variables, t and x, and we have our world of our polynomials in x, and we move between them by taking a polynomial in x and t to our polynomial after we substitute a value in x. Okay, and given a polynomial in one variable, we attach what's called its Galois group over the field q. So the Galois for a polynomial over q. And given a polynomial in two variables, well, we haven't really discussed what it means to take a Galois group of a polynomial with two variables, but I'll tell you that, for example, you can fix one of the variables. We'll fix t and look at the rational function field, a field of rational functions in t. Then, a polynomial with two variables is simply a polynomial over this field, for example, and we can look at its Galois group. Okay. So the question is, if I substitute the value in the polynomial, what happens with the Galois group? And it turns out that if you take that there's a bit more of a general version of Hilbert's irreducibility theorem, which says exactly this. It says that if we have an irreducible polynomial, you have infinitely many substitutions that preserve the Galois group. Okay? So note that this is a generalization of what we did earlier, because we know that F is irreducible if and only if the Galois group is transitive. So if we started with a transitive polynomial, with an irreducible polynomial, we started with a transitive group. If the substitution preserves the group, we'll still get a transitive group, and that will bring us back to an irreducible polynomial. Okay? And modern, like the more general version of Hilbert's irreducibility theorem, and by the way, I think modern proofs of this do like this and what we did previously for the same proof. This is just the difference between a statement that involves Galois groups and a statement that doesn't. And it turns out that we even have a stronger statement. Suppose we have polynomial in many variables, in k variables. We can substitute up to k minus 1 of them and still get infinitely many substitutions that preserve the Galois group. Okay, so I know you guys are willing to shout in and interrupt, but is there like any questions I can assist you with?
I have a question.
Yes.
Maybe it's stupid, but so you're saying that the Galois groups are equal, and then you're saying that's how we know it's the same. It's still irreducible because it acts transitive in the roots. So I'm asking, is it the same set of roots actually? Like, is it clear?
Yeah. Okay. So you can. Okay. So if you go into the technicalities, you can show that you can always exclude a certain number of bad substitutions, and it won't be the same roots, but it will be like you can easily go from one set of roots to the other. Like behind the scenes, you can look at some mapping between fields.
And that mapping will give us the isomorphism of Galois groups?
Yes.
Okay.
Yeah. So let's see if there's anything more I needed to tell you about this slide. Yeah, turns out that not. Okay, so let's see what's the point of having this many variables. So this will be your second example of a Galois group, and this is kind of a brute force example of a Galois group, but I think it's really nice. And now let's try, okay, so I haven't really discussed why Hilbert cared about all this. So originally the motivation came, he tried to find a polynomial whose Galois group was the entire symmetric group. And he managed, I will show you the example. In fact, like if you walk around the street and gather a polynomial, its Galois group will be the full symmetric group, but that's a different issue. But let's build our own our own example of a polynomial whose wait. Oh, okay, we're good. So let's build our own example of a polynomial which yields the full symmetric group. Hang on, just I think I'll be fine. I'm fine. Okay, I'll move this.
Yeah, it's fine.
Yeah. Okay. So let's see. Okay, so I want to construct my own symmetric group as a Galois group. So we'll do the following thing. I told you that the Galois group needs to act on something. So I want to get the symmetric group of degree n. So let's take n parameters, alpha 1 to alpha n. And the symmetric group, like the full group of permutations on n elements, knows how to permute these. And now let's construct a polynomial. Let's look at the product of the n linear factors, x minus alpha 1 to x minus alpha n. And now let's open the parentheses, the brackets, and we can use the other formula to get expressions for the coefficients of the polynomial f in terms of the roots. So we'll denote the coefficients by, there's something wrong with the indexing again. So this should be like a 0 at the bottom. So we'll name our coefficients. And now I have a polynomial whose coefficients are written as some SIs. So I can look at the field of rational functions or the ring of polynomials with variables S1 to Sn. So I suddenly look at this S1 and Sn like variables. And this is a polynomial with coefficients in rationals in S1 to Sn and x. So we have a polynomial, right? They gave you a polynomial, and we have its roots, and we have a group that acts on these roots. So by our convention, by our agreement, you're going to believe me that the resulting Galois group of f over, so this should be maybe be the field and not the ring of polynomials, is the symmetric group. Okay?
Should this be the same? They are finite.
No, okay, yeah. So the point is that it's actually not the same because these Sn, so yeah, so this is a very good question. So no, this should be, there's a mistake here. This should be round brackets. And the reason is like round brackets, they're the field of rational functions and parameters such and such. And the point is if our alpha ones, we started out as just parameters, like they don't live anywhere, they're formal symbols. Then these Sns, they're actually foreign symbols to the rational numbers as well. Like they don't live there. So we have basically the same setting we had before. We have a polynomial in a lot of parameters. And Hilbert's Irreducibility Theorem, the many variable version, tells us that we can, well, specialize and preserve the Galois group. So we have infinitely many polynomials with the full symmetric group as their Galois. Okay, so wait, how am I on time?
5:03.
5:03, nice. Okay, so did we say something about the inverse Galois problem? Okay, so to summarize, so far we basically talked about this idea that we can have our problem, add parameters to it, and Hilbert's or have this situation, not a problem. And Hilbert's Irreducibility Theorem gives us a way of taking substitutions and like getting an getting infinitely many examples in our original setting. So I think it would be a bit rude. I mean, Hilbert did this while studying the inverse Galois problem. So I think it would be a bit rude not to say like 2 words about it. So let's talk a bit about the inverse Galois problem. I'm going off script. So we talked about how we have a polynomial with rational coefficients. And we can fix to it some finite. So the inverse Galois problem asks more or less, if we take a finite group, can we find a polynomial with that Galois group? Okay? And one of the most the things people most use Hilbert's irreducibility for, well, they use it for other stuff as well, but a major use of it is for the inverse Galois problem. So I think my advisor will get mad at me if I say this. They use it for plenty of other things. One of the initial motivation for this was the inverse Galois problem. It's a really important tool in the inverse Galois problem. And the trick is that Hilbert's Irreducibility Theorem allows us to work, instead of polynomials with one variable, it allows us to work with polynomials with 4 more variables. And it turns out that this world is a lot easier to work with in a way. Like, we have more structure, we have more information. Sometimes we can go up to the complex numbers and polynomials in 2 variables, and over there it's even nicer. And this is how a lot of, so the inverse Galois group, the Galois problem is open. There are a lot of groups which people don't know yet how to find a polynomial for, but a bunch of groups that people worked very, very hard to find, they worked with this method. Okay, so that was our detour to the inverse Galois problem. So the last topic isn't really related, but I think after we've spent like the past half an hour or so thinking about substituting integer values in one variable of the polynomial, then the following problem is easier to grasp. So suppose we have a polynomial with integer coefficients and one variable. So if we substitute something in, we'll always get an integer, right? So we can't really talk about irreducibility because it's not a polynomial, it's an integer. But we can talk about something which is in a way analogous to that, which is being a prime. So we can ask, if we have a polynomial with integer coefficients, are there any substitutions such that the polynomial, after plugging, like, are there any values which we can plug in such that the result is a prime? And if so, how many? So suppose our polynomial is 2 of x plus 1, then then our image covers the entire, right? All the odd integers, and we have odd primes. So if you have an odd prime, you can get it through this function. And if we have x squared plus 1, then we can try and plug in several values, and well, some of them will be prime, some of them aren't prime. So these are examples of, well, we're plugging values in a polynomial and ask ourselves whether the result is prime. And there's a conjecture by Bunyakovsky. So there are a lot of generalization to this. This is like the simplest one, I think. But that's the following. That suggests the following. Suppose we have a polynomial with integer coefficients. And now we'll have like 3 conditions, and they're very sensible conditions. So our leading coefficient is positive, our polynomial is irreducible, and suppose we look at all values of this polynomial when plugging in an integer, they have no common factor. Then this polynomial is prime for infinitely many positive integers which you plug in. Okay? So it turns out that like this analog, you have a polynomial, you plug in stuff, when is it prime, how many times is it prime, then it's completely open for polynomials of degree greater than 2. It's even open for the polynomial x squared plus 1, which we really like and just saw in the previous slide. Okay? And so this is like a huge conjecture. It's very, very strong. And I thought it was interesting. So do you have any questions?
Do you want me to ask a very annoying question you know I will ask?
Yeah, we should.
Okay. Is this proven, let's say not that it's prime for infinitely many positive n, but can you say, for example, that it's prime for a positive density of positive n, or some nice set with some nice logarithmic positive density or something?
So I actually have no idea about this conjecture. Basically, the reason I included it here is that I understand it through, like, what helped me grasp it was Hilbert's Irreducibility Theorem. It's like, oh, you can plug stuff here, and but the Wikipedia page, I think, has a lot of information, especially if you look at the more general conjectures, Schinzel's hypothesis H, which is like this one for several polynomials, which leads us to our final point, which is,
Hey, Tali.
hey, Shaked, yeah.
the values f1, f2 have no common factor, is it equivalent to the polynomial being monic, or does
No.
monic imply it? I'm sorry. This is what I was
I don't know off the top of my head, but I'll show you why we rule this out. Like, we don't want some situation where we take I don't know,
2x.
like we don't want something like 2x, and then 2x won't help us, but like that would like something that has this, like if f1, f2, etc. have a common factor, then we get a bunch of noise. Like we instantly have no hope of getting a prime, because if f1, f2, etc. If we have a prime that divides every possible substitution for every possible integer, then so 2x, exactly.
So the only hope to getting a prime is getting p, right? And so we won't only get it one time.
Yeah, exactly. So the only, like you said, thank you. The only hope for getting a prime will be getting p. So if you want to know more about Bunyakovsky's conjecture and its various generalizations, and now I see that you do want to know more, you are welcome to volunteer to give a what is talk about it. So thank you all for coming.